In this video, we will look at some challenging problems where the dimensional analysis process can be used to help us make sense of the units. But first, let's review a conversion example from one rate to another where we have to change 2 units. We are asked to convert 45 miles per hour to feet per minute. So first, identify the units that you have been given and the units that you are trying to change to. Next, we identify where we're starting using our dimensional analysis ladder. We've been given 45 miles per hour, and we are attempting to change that to the number of feet per minute. So miles to feet has to be changed. We have that conversion ratio given to us, but we also need to change hours to minutes. That conversion ratio I expect you to know, but let's just go ahead and write it down. In 1 hour, there are how many minutes? Hopefully you said 60. Okay. Now, we set up our dimensional analysis ladder, starting with what we're given with our undesired units to change to the desired units. So in our next part of our dimensional analysis ladder, we've got to change miles to feet. If I want the miles to cancel, you should put that 1 mile on the bottom and the 5280 feet on top. That's going to cancel our miles, leaving us with feet. And that's what we want on top. Mission accomplished there. Now we need to change the hours to minutes. The hour is originally on the bottom of our dimensional analysis ladder. So our conversion ratio for that, our 1 mile would be on the top. Or hour, sorry, our 1 hour would be on the top. And 1 hour is equivalent to 60 minutes. So now I've got an hour on the bottom, an hour on top. They cancel out. So look at what we're left with, feet per minute. And that's exactly what we want. Now the last step is to do the computation, actually the math to find the answer. So we'll multiply across the top, 45 times 5,280. That gives us 237,600 over 1 times 1 times 60, that would just be 60. For a final answer of 3,960. So there we have it. 45 miles per hour is equivalent to 3,960 feet per minute. And if we're making sense of it, that is understandable. Feet are much smaller than miles, so it's going to take a whole lot more of those. Minutes are shorter than hours, so we're talking about more feet happening over that amount of time. Now let's look at another example using a dimensional analysis ladder. The acceleration of a remote control car is given by acceleration equals velocity over time, v over t. That didn't copy, so I had to write it in there for you. Where v is the change in velocity measured in meters per second, and t is the time taken measured in seconds. If the change in velocity for Johnny's car is 2 meters per second over an elapsed time of 10 seconds, what is the acceleration? Now, that's a problem that's very wordy, and it sounds like a lot going on, but we've been given a formula. Acceleration equals velocity over time. So that's the key. We've been given the information. We are simply going to plug those values into the spots where they belong. We are told in the problem that velocity, the v represents the change in velocity measured in meters per second. Well, they gave me that. Johnny's car, the change in velocity for Johnny's car is 2 meters per second. So for v, we're going to plug that in. 2 meters per second. And remember, per, we use a fraction bar to show the unit or rate. We are also given the t, which is time. They tell us that t is the time taken measured in seconds, and they told us that that change in velocity happened over 10 seconds. So we also have T. Now remember, A equals V over T. So we plugged in V. V happens to be a rate, so we end up using the top and the bottom of our dimensional analysis ladder. And the time is on the bottom. So we're going to plug in T. So this is V and T would be here. But when we plug in the T, T is on the bottom of that fraction in our formula. So in our dimensional analysis ladder, we need to put the 10 seconds on the bottom as well. Now we can answer it. It's just a matter of that. Given a formula, plugging in the values where they belong in the formula, and doing the math. So we got 2 meters on top, and 1 times 10 would be 10. And seconds times seconds, anytime we take something times a unit times itself, we go to the next dimension, or seconds squared. Seconds times seconds is seconds squared. We can also simplify that. 2 over 10, you wouldn't leave it that way. We would reduce that fraction to 1/5. And the unit is meters per second squared. Now, I want us to look at this problem in a different way. What I'm going to do here is take away the numbers. So let's look at this problem. I'll leave the work so we can see it from before. But let's look at this one. Example 2. Very similar. Only thing different is the comfort of the numbers have been taken away. Let's read it. The acceleration of a remote control car is given by, again, that would be A, acceleration equals velocity over time, V over T, where V is the change in velocity measured in meters per second, and T is the time taken measured in seconds. What is the unit of acceleration? So notice the difference in example 1's question. We were actually asked for the acceleration, so we had the numbers to do the math to actually give us a value. But here the numbers are gone and the focus is on the units. Well, how we would approach this problem is the same as we did the first example. If we are given that acceleration equals velocity over time, we know the formula and we know the units. So we're going to plug those units in for each of those values in the formula as well. V is the change in velocity measured in meters per second. So in place of V, no numbers this time, we're just going to have meters per second. So that's our V represented. And T is time, but in the formula, T is in the bottom and measured in seconds. So we put that for T, the seconds, in the bottom of our dimensional analysis ladder. So what do we have here? What unit is acceleration measured in? We've got meters on top and seconds times seconds on bottom. So that's meters per second squared. So this type of question appears to be very challenging and actually quite wordy. But if we dissect it and approach it in the same way we would if we have numbers, we can use the dimensional analysis ladder to help us figure out what the units are as well. Let's look at one more example. And on your handout, it's number 1 in the You Try practice. Body mass index is a measurement of the relative percentages of fat and muscle in the human body. The formula for calculating one's body mass index is BMI equals M over H squared, where M is mass in kilograms and H is height in inches. What is the unit of measure for BMI? So as in the problem before, we have been given a formula, and that's a good thing. Formulas tell us where to plug values in. So the wordiness and the fact that there's no numbers should not discourage us. They tell us that M is mass in kilograms. So in place of the mass, we don't have a number, we have the unit. We're going to put kilograms. And height is in inches. So in place of the H for height, we don't have a number, we have a unit, we're going to plug that in. So instead of height, we put inches, because height is being measured in inches. And guess what? We now can see the unit. There's no canceling that needs to be done for one unit on top of another that's the same. So the measurement of BMI, or your body mass index, is in kilograms per inch squared. That's how the unit for which body mass is measured. You have 2 more problems that I want you to try, number 2 and number 3 on your handout, and we'll discuss and answer your questions tomorrow.